Welcome back to our channel. Today we will see some more question and answers from alkyls, phenols and ethers lesson. The first one is orthonitrophenol is more acidic than orthomethoxyphenol. Give reason for that. Orthonitrophenol. You can see orthonitrophenol, OH N word. This is called orthonitrophenol. This is more acidic than orthomethoxyphenol. Clear? So how we can explain that any given phenols are acidic, as we know. And this orthonitrophenol is more acidic, we have seen previously, because it is having an electron with the trying group in the benzene ring. So it will have minus I effect. This will take the electrons from the benzene ring, then the electrons from the OH comes towards the benzene. Then the bond between O and H, these electrons also pulled like this, such that H can easily leave as H plus ion. So in an acid, if the hydrogen is easily able to leave as H plus ion, then it is more acidic. So minus I effect says that nitrophenol is more acidic. Acidic here. We will see the another one, then we can tell whether it is more or not. But when compared to the phenol, nitrophenol is more acidic, because phenol, since O is electronegative, it pulls the electron, so H can easily loses. But in nitrophenol, the pulling nature of this electron density towards the benzene ring is further enhanced, increased, because of the electron with the trying group called NO2. NO2 also takes the electrons, so that benzene ring will have less density, then benzene ring will take the electrons from OH bond. Then H loses as H plus ion. This also can be explained by another way, where minus R effect. So both minus I effect, I is inductive effect, R is resonance effect. Clear? So if I can take O and hydrogen, and O will have two lone pairs of electrons, and here nitrogen and double bond O, and another one dative bond, so it is negative, it is plus. This way we can write N. So because of the resonance effect, what will happen? This nitrogen positive and OH, and this is O. So now because of I effect, this is taking the electrons. Even in the R effect, these electrons were given like this, and this bonded will be there. That means this lone pair participate in the delocalization. So you will be getting different resonance forms. So now you will have another structure, and these two are not changed. You can write like this, simplify. Then O, hydrogen bond is as it is. O has lost two lone pair of electrons, one, so it gets positive charge, and here I have double bond. And this double bonded one, N, double bond O, and O is minus, this is plus, this double bond came here, so there is a minus charge over here. This is one resonance form. So we can continue the resonance forms. Another resonance form I am writing here. What happens? This double bond will be moving toward between the carbon and nitrogen. Then this bond will go to the ox. So this is the next resonance form. So the unchanged things can be written first. Here double bond O and hydrogen. O is having positive charge as per this, as it is we are writing, there is no change. And here we get now double bond N. Then this bond becomes negative, and this is already negative and plus. So this is the form, because this went here, then this bond went to the next one, negative charge. So now if you can see this resonance form, next one what will happen, this comes here and these moves like this. Then you can write all these resonance forms. Previously we have written in our previous video how this will be done. If the negative charge is on the carbon, send inside and our bond will be moved to the next. So the resonance will continues. In these resonance forms, you can see our oxygen gets positive charge. That means electron density at the oxygen is less. So it also enhances. Then what it will do? Enhances the less number of electron density, the effect of pulling off the bonded electrons towards the oxygen. That means hydrogen can easily leave as H plus ion. If it is leaving as H plus ion, it is called as acidic. So the nitrophenol is more acidic because of two effects. One is minus R effect, resonance effect, and one is minus I effect. These are the two effects by which R effect and I effect, the nitrophenol is more acidic than phenol. And another way also we can tell, there is another one. You see, if any acidity, if you want to explain, first we need to see what is acidity, because if it is loses H plus ions, it is acidic. For example, consider that it loses H plus ions. So then what I will get after losing the H plus ion? If you can see, I have 3 bonds here. Once the H plus goes, I will get O minus. This is called phenoxide ion. So now I have a nitro group, so nitrophenoxide ion. So this happened because of H plus ion left. So if the reaction happened this direction, forward direction, then I can say this is more acidic. If the reaction should happen like this, then the product should be more stable than the reactant. That means I need to see that whether nitrophenoxide ion is more stable or not. So this nitrophenoxide is stable. It gets stability by resonance effect. What happens? Once again it gives the electrons like this, and these electrons will participate in the bonds. Similar resonance forms can be written like previously we have written. So it comes double bond here and here negative charge. The next time this negative charge goes here and these electrons goes negative charge. Then next this will come and these electrons will. So like this it can continue the resonance form. That means we are telling here phenoxide ion, that is nitrophenoxide, better. Nitrophenoxide ion is more stable because of the resonance effect, such that so the nitro or the nitrophenol easily loses H plus, so it is more acidic. So this is the way one can able to tell whether it is acidic or not. Then another one is methoxy nitrophenol. That's what the next question. Next one, they ask to compare with methoxy phenol. Methoxy group, you know, this is OCH3, sorry. So now I have oxygen and hydrogen. Then another one is OCH3. Previous one we have electron withdrawing group nitro, but now this is electron donating group, electron releasing group. If electron withdrawing group type, what happened? The electron density on the benzene was less, such that the electrons it pulls from the OH bond, so H can easily lose. But now this will give the electrons. So if it I effect is opposite now, so it gives the electrons, more number of electrons here, so it will not take the electrons from the hydrogen so easily. So H cannot leave as H plus ion. So that's why the acidity of methoxyphenol is lesser when compared to the nitrophenol. Okay, this is the way we can able to understand this particular compound. Even we can also write another one, the phenoxide ion which forms will not get stabilized. For example, if I take this phenoxide ion after losing the H plus, it will not get stabilized. Once again it forms this type of bonds only. Since if I get this is the resonance form, then what we will be getting? So here double bond, here the single bond and O minus, this OCH3, here I have double bond because this went and formed the double bond, so it gets positive charge. This double bond moved to this carbon negative charge. Now, like this, you can this resonance form. If you can see, these two are resonance forms. If you can see, there is a negative charge nearby two atoms, adjacent atoms. Carbon is having negative charge, oxygen is having negative charge. They will be repelled each other. So this form is not possible. It is unstable. We can also tell based on the type of resonance form whether it is stable or unstable. There are certain rules. So here also you can see the negative charge held by oxygen is acceptable, but the carbon is having negative charge. It is less electronegative. It cannot hold the negative charge. Even if it holds and there is a negative charge are nearby, so they will both repel each other. So this structure will get unstabilized. So the resonance structure is not fully stabilized. So methoxy phenoxide ion is not stable. So that's why it cannot easily lose the H plus ions. This is one question. Next one. Describe the mechanism of alkyls reacting both as nucleophiles and electrophiles in their reactions. So alkyls acts as both nucleophiles and electrophiles. That's what they ask to explain. Alkyls acts as both nucleophiles and electrophiles. How it happens? See, alkyls, there are COH. If the H loses, that is OH bond gone away, that is H goes as H plus ion, then we will get R minus, so it acts as a nucleophile. O minus, so HS goes, then O minus, then it acts as a nucleophile. So for example, it is methyl group, hydrogen, something. This is the compound. What will happen? It can act as a, for example, I have a carbocation and now I reacted with ROH. Then what will happen? This O will come and attack as a nucleophile. This is the nucleophile because oxygen is having lone pair of electrons. And oxygen is more electronegative and this bond becomes more negative here, positive here, polar. So what should happen generally? This ROH, where since it is having lone pair of electrons, it can act as a nucleophile and it attacks here. Once it attacks here, then you will get ROH. Correct? This forms the bond with carbon. So I have carbon bond and all three sides remain. So then this oxygen lifts it, so it gets a positive charge. Clear? This have asked the two electrons to bond with carbon. These are the two electrons. So it gets a positive charge. So this is the nucleophilic attack to a center, which is nucleophilic center. Otherwise it is a carbocation, positive charge. So a nucleophile comes and attacks here. So alkyls acts as a nucleophiles. Then what will happen in the next step? It takes these electrons and H plus loses and you will get ROC bond, or that is ethers, ROR bonds. ROR bonds. So these are called ethers. You can get it. So this is the nucleophilic attack. The bond between O and H gets broken when alkyls react as nucleophiles. So the bond between this O and H gets loosened. So you will get a bond between O and the next carbon. These are the where the alkyl acts as a nucleophile. Similarly, the bond between C and OH gets broken when they react as electrophiles. So next time what should happen? If they want to if they react as electrophiles, the bond between here will be broken. Now in nucleophiles, the bond between here broken, nucleophiles. If it is electrophile, it acts, then the bond between here is broken. Because OH minus can lose, then C becomes a positive charge. So it is a methyl electrophile. So that's also we will just try to see. So another case is we are seeing now it acts as an electrophile. We will take example RCH2OH. So this is the alcohol, and if it acts as electrophile in presence of acidic catalyst, for example, if it has a protonation H plus, then what should happen? RCH2 OH, this H plus will come, so OH2 plus, OH2 plus, or CH2 OH2 plus, that is protonated alcohol. So once it is a protonated alcohol, so now this protonated alcohol I am writing RC OH2 plus and H and H. The same was written like this. So now you can take any nucleophile and nucleophilic attack, because it loses as H2O, so then the nucleophile can come and attack to the carbon. In this case it acts as a now electrophile. So the bond between C and O is broken now, and you got a new bond between nucleophile and carbon. So nucleophilic substitution happens, so it acts as a electrophile. Electrophile. So then I will get R C H H. Better to write R this side, and this side you can write Br. So this is the compound. So now what happened in this particular case, when it acts as electrophile, the bond between carbon and oxygen is lost from the alcohol, broken. Previously the bond between O and hydrogen was broken. So this is the way the electrophilic Br minus, whether you are able to see or not, Br minus here. So this is the way we can explain that alcohols can act as both nucleophiles and electrophiles, So next we will see some conversions, as in previous videos we have seen some conversions. We will try to do this some more. Benzoquinone from phenol. The next conversion is benzoquinone from phenol. How to get benzoquinone from phenol? You see, if I take a phenol, conversion of phenol to benzoquinone. Phenol to benzoquinone. I have phenol. You may know the benzoquinone. Phenol. So this is the reaction where you need to get oxidized the phenol. The phenol, if it is oxidized at para positions, then you will get benzoquinone. So you need to have an oxidizing agent. Remember here it can be done sodium dichromate and H2S4 in presence of Na2Cr2O7, oxidizing agent, and acidified H2S4, then you will get the benzoquinone. And this is the way we can able to convert phenol to benzoquinone. You need to remember H has to be removed and both carbons need to get oxidized. So you need to use sodium dichromate, then you will get the benzoquinone. This is the conversion of phenol to benzoquinone. And another conversion is phenol to salicylic acid. Phenol to salicylic acid. Phenol to salicylic acid, that is ortho to hydroxybenzoic acid. So if you have phenol, phenol is OH. Now salicylic acid is COH group at the ortho position. So it can be reacted with aqueous sodium hydroxide. Aqueous sodium hydroxide, NaOH, with CO2 and acidified, then you will get OH and COOH. So you also will get a para product, but this is salicylic acid. You can also get 4-hydroxybenzoic acid. On the para position you will get the COH group, but major both ortho and para both are possible in this particular case. If you want to prepare the same, then we can, this reaction is also called as uh, we will do Kolb's reaction. Kolb's reaction. So here we will write the stepwise things. So now we have phenol can be reacted with aqueous NaOH. Then what will happen generally when I react with aqueous NaOH? Phenol is acidic and basic, so you will get a salt of sodium phenoxide. O minus Na plus, that is the sodium phenoxide. That is the first step. Then you see what will be left over. This sodium phenoxide can be further treated with this. Okay, here sodium and here O and here, and water is left, H2. Okay, H2. Now this sodium phenoxide can be further treated ONA plus minus with CO2. CO2 and 400 Kelvin. 400 Kelvin. Whenever the gas is there, there should be some pressure we need to maintain. Gas is 4 to 7 atmospheric pressure. So the sodium phenoxide can be treated with CO2. Then you will be getting the CONA, that is the compound which is just the CO will be added to this compound. You can see this is phenol and O here COONA. So the CO2 group goes and attacks here, and we will get CON here. This is acid salt. So that is the way you will be getting. This product will be rearranged, undergoes rearrangement. OCOO minus Na plus. It gets rearrangement. It gets rearrangement like this, OH, and here this particular one COO are the position. So this is the way it gets rearranged. So COO and here C it is COO minus Na plus. So once this happens, then finally what we should do? We should acidify the compound. If you are acidifying the compound, you will get this OH COO Na, salt will be acidified as acid. So you will be getting salicylic acid. This reaction is Kolb's reaction. Kolb's reaction. Kolb's reaction. So when sodium phenoxide generally heated with CO2 at about 400 Kelvin and under 4 to 7 atmospheric pressure, sodium salicylate is found. What we got is sodium salicylate. That sodium salicylate further acidified, then you will get the salicylic acid. So this is the salicylic acid, this is sodium salicylate. So this is the way phenol can be converted into salicylic acid by Kolb's reaction. I hope you understood. So now I have phenol. It was treated with aqueous sodium hydroxide. Then you get sodium salt of the phenol, that is sodium phenoxide. The sodium phenoxide was further treated with CO2. CO2 comes and attacks here. There is mechanism, but we are not discussing much here. For simplicity, we are finishing here. When the mechanism solves, we will discuss at one time. So O minus Na plus, so CO2 comes and OCOO Na plus. This is the one which gets rearranged. That means the group will move towards the other position, and other position it attacks. Then OH comes and COO Na, because there is a hydrogen here. Hydrogen moves to O, and this particular group comes and attacks the carbon. So CO minus Na plus, sodium salicylate. Sodium salicylate can be acidified, and you will get the salicylic acid. So this is the way the conversion can be done. Similarly, if you want to get salicylaldehyde, this is salicylic acid. If I want here CHO group, I hope this we have seen in the previous video, but okay, we can just go through fast. So the phenol can be converted into sodium salicylate. So that can be done by using chloroform and aqueous sodium hydroxide. So now I have phenol. So can be treated with CHCl3. Chloroform CHCl3 in presence of aqueous sodium hydroxide. Aqueous NaOH. Instead of their CO2 here we will CHCl3. So then you will be getting OH, then CH. This is salicylaldehyde. This is the salicylate. 2-hydroxybenzoaldehyde is called salicylaldehyde. Anyhow, we will get sodium salt of the salicylaldehyde. If you can acidify it, then you will get the salicylaldehyde. So this is the way we can able to convert this phenol to salicylaldehyde. So another one they have given, phenol when we react with bromine water, what is the byproduct? But what is the product we will get? Phenol when reacted with bromine water, that is bromination. Bromine water is bromine, aqueous bromine. They can ask two ways, one is bromine water or aqueous bromine. So when phenol reacted with bromine water, what will happen? It is a electrophilic substitution, but the substitution happens completely. That is 3 bromines comes and sits at the ortho and para because it is a ortho para directing group OH. OH is ortho para directing group. That means OH sends the incoming electrophiles to ortho and para. That how you will be knowing already by if you write resonance forms you can understand. So this is para position and this is one ortho and this is another one. So tribromophenol. So 2,4,6 tribromophenol is the product we can get from this particular reaction. And similarly they also ask butane 2,1 to butane 2-ol. So I hope this you understood. Fully complete bromination happens here. Then another conversion they asked is butane 2-ol. Butane 2-ol 2,1 that is ketone. Butane 2,1 to butane 2-ol. Butane 2-ol. So that ketones to alcohols. You remember a general condition, general understanding that alcohols ROH can convert to carbonyl compounds. Carbonyl compounds are aldehydes and ketones. So alcohols to aldehydes ketone, that is C double bond O. H or R. In aldehydes is H1, ketones R, but other one is R, must. Or even H for the formaldehyde case. So ROH to RCO. What happened here? One hydrogen is less. So these are called as alcohols to aldehyde. Removal of hydrogen or addition of oxygen. They are all called oxidation. So alcohols oxidizes to get carbonyl compounds, aldehydes, ketones. They further oxidizes to get carboxylic acid. They further oxidizes to get carboxylic acids. So now we are going backwards. A ketone is converting to alcohol. Ketone to alcohol. That means it is a reduction. It is a reduction. So you need to have a reducing agent. We need to understand that a reducing agent. Butane 2,1 we can able to first try to write CH3. Okay, previous way we can write just for understanding. Butane is 4 and second position is one group, one is keto group, remaining is hydrogens, that's all. So CH3, CH2 and CH3. This is butane 2,1. Now I need to convert into butane 2-ol. That is second position I need to have OH. correct? Here H should come, here H should come. Both hydrogens, if it comes, it becomes CHOH. So that is the butanediol. You can see like this. So we will write butanediol simply. Try to write 1, 2, 3, 4 carbons, and second position is the OL group. So you can write OH group here. Then this is CH3. This is one H here. This is H2 here. This is H3. Because remaining carbon 4 to satisfy its 4 valency, we need to give the hydrogens. So this is butane 2,1. It is butane 2. So I need to have only hydrogens. So that's why I told it is a reduction reaction. That reduction can be done in presence of lithium aluminum hydride. It is a reducing agent. Lithium aluminum hydride. This is one of the reducing agent. Using this reducing agent we can do, or nickel in hydrogen. Nickel in hydrogen gas. So both can be used as a reducing agent. Okay, we will see some more questions in the next video. Thank you.